Okay, let's get into this. We're doing a deep dive on a mission that honestly sounds like it came straight from a military lab.
Well, in a lot of ways it did, but it also managed to completely rewrite our understanding of the moon and really how we even approach exploring
We're
space.
talking about Clementine,
Yeah.
launched back in 1994.
And that date, 1994, is so important. You have to realize it was the first American spacecraft sent to the moon in over 20
Oh,
years.
20 years. That's an entire generation. We just stopped going.
We completely ignored it. And the reason we went back wasn't, some grand scientific calling. It was very specific.
Right. This thing had a dual purpose.
Yeah.
And the primary mission, the number one job, came from the Department of Defense.
Exactly. The Ballistic Missile Defense Organization, or BMDO, they needed to test a bunch of new super lightweight sensors and spacecraft parts out in a real deep space environment.
And the science was, what, a side quest?
Pretty much. The secondary goal was, okay, while you're out there, get us a full map of the moon with these new cameras, and if you have the gas, swing by an asteroid on your way home.
So that's our mission for this deep dive. How did this small military tech demo end up launching a revolution in lunar science and creating a whole new philosophy for space exploration that we still follow today?
It's a fascinating story. Clementine really set the stage for everything that came after.
The fact that it was a joint mission between the DoD and NASA
Yeah.
that really tells you everything about the money situation in the early 90s after the Cold War.
Absolutely. The days of the blank check Apollo-style budgets were long gone. The whole landscape, geopolitically and fiscally, had just changed.
So they needed to prove out this new hardware,
Yeah.
but they had to do it fast and cheap.
Ruthlessly fast and cheap. And that forced them to challenge the whole paradigm of how you build a space mission. It was all about fixed resources, rapid development, get it done, get the data, and don't worry about making it last for decades.
And when you say rapid, the timeline is, it's just shocking.
It is. The sources say it was designed, built, and launched in less than 2 years.
22 months. From an idea to sitting on a launch pad heading for the moon.
And the cost was the other side of that coin. Less than $80 million.
Which, for a lunar mission, is basically nothing.
It was unheard of. And that combination, that speed and efficiency, made it the poster child for what became known as faster, better, cheaper, FBC.
Right, FTC. We hear that all the time now.
Mm.
But this was kind of the proof of concept.
This is the proof of concept. It showed NASA that, small, super capable satellites could be built and flown for a tiny fraction of the traditional cost.
And that directly led to programs like the Discovery missions, right?
It set the template for them, these rapid, high science missions with a strict budget cap. That all comes from Clementine.
I have to ask about the name, though. Clementine. It sounds so gentle for a military-backed space probe.
It's actually a bit of a dark joke from the mission team.
Oh.
It's from the old folk song, "Oh My Darling Clementine." The spacecraft was going to be mining the geology of the moon,
Okay, that part makes sense.
but it only had enough fuel to do its job and nothing more. So after the mission, it would be lost and gone forever.
That's brilliant. A perfect wry nod to its whole purpose. This is a single-shot mission. High risk, high reward.
And that organizational model was innovative too. The Naval Research Lab handled almost everything: design, build, flight ops. They proved a small, focused, non-NASA team could pull off an incredibly complex deep space mission.
So to do all of this, a full lunar mapping campaign on that tiny budget, it all came down to the engineering.
Radical engineering. The main goal, remember, was to test 22 new lightweight technologies for missile defense. The science was just what you could do with those new toys.
And the big constraint was mass. Everything had to be as light as possible. I think the sources said the dry mass was only 227 kilograms.
That's right. Think about a big industrial refrigerator. That's about the size and weight we're talking about.
And they crammed some of the most advanced instruments of the era into that tiny package.
They had to. Every single component was a prototype designed to save weight. Take the power system. They used these new gallium arsenide on germanium solar cells.
What was special about them?
They were the thinnest ever flown, just 0.14 millimeters thick, paper thin.
And that was purely for mass savings.
Primarily. It saves mass, it lets you pack them more densely. It's exactly what you'd want for a fleet of tiny interceptors like brilliant pebbles. And it was paired with this new lightweight nickel hydrogen battery. Every single piece was pushing the envelope.
That philosophy must have extended to the computers, too. I mean, how do you handle all that data and fly the spacecraft autonomously in 1994 on a shoestring budget?
They used a really smart dual processor system, a basic military standard processor just for, keeping the lights on.
Housekeeping.
Right. But for the real work, the image processing, the autonomous navigation, they had a much faster 32-bit RISC processor.
And that autonomy is key to the whole FBC model, isn't it? The spacecraft can figure out where it is and where it's pointing by itself.
Then you don't need a huge team of people on the ground flying at 247. It saves a ton of money.
So how did it navigate?
The navigation system was amazing. It had these two miniaturized star tracker cameras. They would take pictures of the stars, and an algorithm would match the patterns to a star map to figure out its exact orientation.
And the accuracy was incredible, something like 0.03 degrees.
Phenomenal for a cheap satellite at the time. It also had these new kinds of gyros, a fiber optic one and a ring laser one, as backups.
So the big takeaway here is that the military's need for small, smart, lightweight tech is what made the science mission possible in the first place.
It directly enabled it, and it let them pack in other cutting-edge stuff, like a 2 gigabit solid-state data recorder, which was huge for the time, and an image compression system from the French Space Agency.
So with that whole lightweight toolkit, Clementine gets to the moon and starts its main science phase.
Yep. It spent 71 days in a polar orbit, whipping over the North and South poles every 5 hours. It did that almost 300 times.
And the goal was to create the first ever complete global digital map of the moon.
A goal it absolutely achieved. It sent back almost 1.8 million digital images, covering 99.9% of the surface. But they weren't just snapshots. The cameras could see in different colors, from ultraviolet to near-infrared.
And that's how you start to do geology from orbit, by looking at how the surface reflects different kinds of light.
Exactly. They chose very specific color filters to look for the chemical fingerprints of certain minerals. For instance, they had one filter at 415 nanometers that's really sensitive to titanium,
Okay.
and another one at 1,000 nanometers that could pick up the signature of iron.
So by mapping iron and titanium all over the moon, they could test some big theories.
They could test the biggest one, the lunar magma ocean hypothesis.
Break that down for us.
The idea is that when the moon first formed, it was a giant hot ball of molten rock. As it started to cool, the lighter minerals, specifically a mineral called plagioclase, would have crystallized and floated to the top.
Like cream rising in a bottle of milk.
A perfect analogy. It would form this thick, bright, global crust. And the heavier stuff, rich in iron and titanium, would sink.
So what did Clementine find?
It found textbook evidence for the theory. The dark plains, the Maria, were full of high titanium basalts, exactly where the heavy stuff should have ended up. And even more dramatically, the highlands on the far side, they were almost pure anorthosite.
The rock made of that lightweight plagioclase?
Precisely. It was the smoking gun for the magma ocean. But Clementine didn't just map chemistry. It gave us our first truly detailed 3D map of the surface.
Using its laser altimeter, the LiDAR system.
Right. The LiDAR measured the height of the terrain with a vertical resolution of about 40 meters, and that led to arguably its most famous discovery, mapping the full scale of the South Pole Aitken Basin.
This SPA basin. Just give us a sense of the scale here. We're not talking about a normal crater.
Oh, not at all. This is the biggest, oldest, and deepest impact basin on the moon. It is enormous. About 2,500 kilometers across. That's like the distance from New York City to Denver. And the LiDAR data showed it's incredibly deep, 12 to 13 kilometers deep in places.
And what does knowing its shape and depth tell you?
It lets you figure out how thick the moon's crust is. The data showed that beneath the SPA basin, the crust is only about 30 kilometers thick, compared to a global average of 50 or 60.
So the impact that created it was so violent it just punched right through most of the crust.
Exactly. It dredged up material from the deep lower crust, and maybe, just maybe, from the upper mantle itself. It's a natural window into the moon's interior.
So while the LiDAR is mapping ancient history, the science team decides to try something a little more improvised.
Very improvised. They wanted to look for something vital for the future of humanity in space. Water ice.
But Clementine didn't have an ice detector, did it?
No, not a dedicated one. So they came up with this clever hack called the Ballistic Radar Experiment. They used the spacecraft's main communications antenna.
The one that used to talk to Earth.
Right. And they pointed it at the moon's poles, specifically at the craters that are in permanent shadow, the PSRs. They beamed a radio signal down into them.
And the Deep Space Network antennas back on Earth listened for the echo.
Yeah.
But how does a radio echo tell you if there's ice versus just rock?
It's all about the polarization of the signal. The signal they sent had a specific circular twist. Now, if that signal hits normal, dry, rough rock, the echo that comes back is all scrambled. The polarization is random. But if it hits water ice, something special happens. The signal penetrates the ice a little, bounces around inside the crystals, and comes back with its original twist mostly intact.
So they were looking for this specific kind of reflection that screams ice.
They were. It was a total Hail Mary experiment. And the initial result, which they announced in 1996, was tantalizing.
What did they find?
The data showed a signal consistent with the presence of water ice. The estimates were on the order of, a small lake's worth of ice locked in the soil.
That's a massive discovery. But I imagine, given that the experiment was improvised with military hardware, there was a lot of pushback from the scientific community.
Oh, the scrutiny was intense, and rightly so. Other scientists pointed out that you could potentially get a similar-looking signal from just really rough terrain inside the craters. The data was suggestive, not definitive proof.
So it wasn't a slam dunk.
Not at all. But that ambiguity was actually its greatest contribution.
So.
Because it put a giant scientific bullseye on the lunar poles. It made everyone realize those permanently shadowed regions were the most important real estate on the moon. It directly motivated the next wave of missions, like Lunar Prospector and LCRS, which went back with the right tools to confirm it. Clementine basically kicked off the lunar water rush.
And that brings us to the mission's end. We talked about the risk inherent in faster, better, cheaper. And that risk finally caught up with Clementine after it finished its lunar mapping.
It did. The plan was to head off to the asteroid 1620 Geographus. But on May 7, 1994, there was a computer glitch.
A software bug.
Seems so. It caused one of the attitude control thrusters to just turn on and stay on. It fired for 11 minutes straight.
And on a mission with absolutely no extra fuel.
11 minutes was all it took. It used up all the remaining propellant and sent the spacecraft into an uncontrollable spin, tumbling at 80 revolutions per minute. The asteroid flyby was off.
Just a heartbreaking end to such a successful mission.
It's the double-edged sword of FBC. You build it fast, you build it cheap, but you have very little margin for error. And the political fallout was frustrating, too. There was a follow-up mission, Clementine 2, that was fully approved.
But it got canceled.
Canceled by a line-item veto in 1997. A $20 million mission that would have visited multiple asteroids was used as a political football to show fiscal responsibility.
But even with that ending, its legacy is just immense. That data is still foundational.
Absolutely. Clementine's maps are still the baseline. Missions from Japan, from India, they used Clementine's mineral maps as their starting point to refine the science.
And for today's exploration, it's even more relevant. NASA's Artemis program, all the commercial landers, their entire strategy is based on Clementine's polar data.
It's all about the PSRs, the permanently shadowed regions, and the nearby peaks of eternal light where you could put solar panels. Clementine put those on the map.
So really the water. Even though the initial finding was controversial, that hint of a resource changed the moon from a place you visit to a place you might stay.
It turned it from a scientific curiosity into a strategic asset. The entire debate about where to build a lunar base is driven by the maps Clementine made 3 decades ago.
What it all comes down to then is that this mission was a kind of technological Trojan horse. A cheap military test flight that accidentally kickstarted a new era of science.
It proved that small, focused teams could do incredible things, but it also showed the risks of that model.
And that legacy, the most important piece, is the resources. It gave us the first real hint that the materials needed for humanity to live off-world might just be waiting for us right next door.
Making travel to and from the moon and even beyond much more routine.
And that's a final thought to leave you with. Clementine opened the door to the moon, becoming essentially a gas station in space. If you can mine that ice and crack it into hydrogen and oxygen rocket fuel, the entire economic equation of space exploration changes. So what's the long-term geopolitical significance of that one single ambiguous finding?
It has the potential to turn lunar soil into the new oil.